Okay, well, thank you for that introduction. So I'm from the University of Tennessee, Oak Ridge National Laboratory, and also the University of Manchester, where I have a position in the math department. What I want to do is to look at high-performance computing and talk about some of the issues that we're facing as we go forward. But first, I want to look at the top 500 results. So I'm one of the authors of the top 500, along with Horst Simon and Eric Strohmeyer. The top 500 lists the 500 fastest computers, and they're ranked according to a benchmark. That benchmark is called the LINPACK benchmark, and the benchmark is solving this linear system of equations, AX equals B, where the matrix A is a dense matrix, and the idea here is to make that matrix as large as possible, solve it using Gaussian elimination with partial pivoting, that's part of the rules, and compute a solution. The solution has to be computed to 64-bit accuracy, and there's certain rules about how one has to do that. But typically what we see is as we increase the size of the matrix, the rate of execution goes up until you reach some asymptotic point. We want to capture the asymptotic point for your machine. So that's the goal. This list is updated twice a year at this conference and at the conference that's held in Germany. So this, in some sense, is a historical view of supercomputing for the last 25 years. So we have 25 years of data on that benchmark looking at high-performance computing. Up at the top there in red is the fastest computer, 93 petaflops. So 93 times 10 to the 15 operations per second as run on the benchmark. The green guy is the guy at the bottom of the list. That's machine number 500. So 548 teraflops, or a half a petaflop roughly, is the entry point for supercomputing, if you will, today. And that number 845 is the sum of the 500 computers. So that's an artificial number, just adding things up. So you can see how things have changed over time. You know, it's interesting to note that the guy that's at the bottom of the list today was equal to the sum of all the computers back in 2003. So things are changing very rapidly. You know, to be on the list and be number one and to fall off the list takes about 6 years. So you make an investment in the fastest computer, and that machine costs roughly $200 million, and after 6 years, it's not even considered a supercomputer. So you have to make this continual investment in high-performance computing. My laptop, that machine there, I can run the benchmark on. And when I run the benchmark, I get 166 gigaflops. 166 gigaflops, if we look back on the top 500 list, that was faster than the fastest machine back in 1995. So that's an incredible situation we're in terms of computing, in terms of processing. This is a look at that same set of data, but now trying to extrapolate out. If we take a look when we reached a teraflop, that was in 1997. So we had 10 to the 12 operations per second on the ASCII red machine. About 11 years later, we reached a petaflop, and that was at the Los Alamos Roadrunner system. And we anticipate that we'll be at an exaflop, another 3 orders of magnitude, roughly in 2020. The Chinese say they're going to get to exaflop in 2020. That's a stake in the ground they've already put. In the US, the plan is for 2021 to have the first machine. If we take a look at how things have changed, you know, a Knight's Landing or the Shenwei processor, the one that's in the number one machine, runs about 3 teraflops. So that's the performance of one chip. That's equal to that whole machine back in 1997. One rack of that number one machine is about a petaflop in performance. So again, you see this rapid change that's taken place. Here's sort of a look at high-performance computing today. Today we have machines which operate at a petaflop. There are 181 systems that are operating over a petaflop in performance. We see 3 technologies emerging with high-performance computing. One is taking commodity processors, taking a lot of those processors and putting them into a box and connect them together somehow, maybe with InfiniBand or Gigabit Ethernet, and call that a supercomputer. The second way is to take those same commodity processors together with an accelerator, like Nvidia, and put them together in a box and connect them together, and we're going to call that a supercomputer. And the third one is to use lightweight cores. So think about cores that don't have all the sophisticated logic, let's say of a Xeon processor, look-ahead instruction, prefetch, and issues like that. So there's a number of processors which are very lightweight, the IBM's Blue Gene, ARM processors, Knight's Landing, the Tahoe Light, and the PZ processor, those guys over there behind the DOE booth have very lightweight cores, and those make up a certain architectural class. We see high-performance computing being used worldwide. Today, if you take a look at this list of the 500 fastest computers, about half of the machines are in industry. So industry gets it. These machines provide some kind of competitive advantage for them, and they make that investment to help build better products. Exascale computing, there's many projects that exist today that are striving to get to exascale, and we see that in the US, Japan, China, and also in the European Union. Intel, if you take a look at the 500 computers, we see Intel processors in 94% of them, and another 1% with AMD. So x86 architecture really is driving high-performance computing to an extreme. This is a chart of the 500 computers. So there are 500 rectangles. Each rectangle represents a computer. The area of the rectangle gives you a sense of the power of that computer. So this guy here is the fastest computer. And this guy's the number 2 computer. And this guy's the number 3 computer. And you can go down the list. Today, China has 202 machines on the top 500 list. 202. The US has 144. That's the lowest point for the US since we've been collecting this data over the past 25 years. So that's a striking thing. Here's a list of the 10 top machines. The guy at the top, the number 1 machine, is the machine at the National Supercomputing Center in Wuxi. That's a Sunway Tahoe Lite. They built their own chip. They built their own network. They built their own software. That's a total Chinese machine. It has 10 million cores in it. 10 million cores. So if you're going to program at scale, you need to be managing 10 million threads of execution on that machine. 93 petaflops is the performance. That's 74% of the theoretical peak performance. They consume 15 megawatts under load, and that gives them an efficiency of 6 gigaflops per watt. You want that number to be as high as possible. And you can scan down the list and see what's happened there. Here's a machine of interest. It's built out of this accelerator. It has 19 million cores, right? These are cores. They're not CUDA cores. These are real, actual cores sitting in the machine. So that's a stunning number. They achieved 19 petaflops, 67% of the theoretical peak. And notice their power consumption, 1.3 megawatts. That's a very low number, giving them a very high efficiency. So if you have a chance, their booth is just down the ways here, and it's an interesting machine to look at. So we see Nvidia in a number of machines in the top 10. If you go down the list, of course, there are many more. That machine, that's number 1. You have to add up the next 4 machines to get to that point. So it's a stunning, high-performance machine. If you add up all the machines in the Department of Energy that are on the top 500 list, it's about equal to that 1 machine. And Department of Energy has made a big investment in high-performance computing, so you can see the effects. So I want to talk about some linear algebra software. So we have a package called Magma that we're developing that runs on GPUs, specifically designed for that. And it solves linear systems of equations. It does least squares problems. It does eigenvalue problems, singular value decomposition. And that's available today for solving dense matrices on the accelerated platform. If you take a look at the performance for doing, let's say, an LU factorization, and we're going to look at the performance on a number of platforms. On a Haswell, which has 20 cores, we get performance that's about this range. On the Kepler processor, using our software, we get a performance that looks something like this. Using the Pascal accelerator, we end up with performance like this. And Volta, of course, is giving us the biggest performance. So it's 10 times faster than we would see on that dual socket Haswell processor. Really quite an impressive improvement in terms of the performance. This is a big deal, right? Deep learning is a big deal. It's going to have a major impact in terms of computing. For computational science, it's going to be a tool that we use to help us in terms of getting a better approximation to our solutions. It's not going to give us the solution. It's going to help us in getting there. So it's one of the tools that we will use to get to that point. So deep learning requires not 64-bit arithmetic, not 32-bit, but most likely just 16-bit floating point arithmetic. As a result, we've seen a number of vendors with products in that space. So Intel has something, AMD has something, and Nvidia's processor and the Volta has something which, if used correctly with 16-bit floating point arithmetic, gives up to 120 teraflops of performance. So that's something, you know, from my standpoint as a person developing a numerical library, I want to try to tap into that and use that half precision if I can. There's a lot of constraints with half precision though. So today we have double precision, single precision, and now half precision. Half precision has 16 bits associated with it. There's an IEEE standard for floating point arithmetic using that. But the constraint here is the largest number that you can represent in half precision is the number 64,000. Anything bigger overflows. So you really have to have a short dynamic range for your numbers in order to effectively use that. Again, Volta has the ability, has hardware to deal with that. So of course they have double precision hardware. That hardware has a peak performance of 7.5 teraflops out of that double precision. Single precision, through the FMA instructions, give 15 teraflops, so double. That's typically what we see. 16-bit arithmetic using that same bit of hardware, the FMA thing, gives you, again, a factor of 2, 30 teraflops. But if you use their special tensor core, which is really a 4x4 matrix multiply in 16-bit arithmetic, the performance you can get goes up to 120 teraflops. So you see the big difference there between these two. And you want, you know, for the deep learning, they can get by with this kind of operation. A matrix multiply, the exact operation is A times B plus C, storing it into D. And there's some accumulation that happens in that operation which can help. So two inputs, 16-bit inputs, multiplied together, added, gives you, and that addition turns out to give you a 32-bit answer. And that 32-bit answer can be accumulated. So you can get a little bit more precision than perhaps you deserve using that 16-bit operation. So here's the performance for matrix multiply. This is on the Volta. This is looking at matrices, large matrices, square matrices, and looking at the size of the matrix here, looking at the performance. This is double precision, 64-bit arithmetic. Single precision, you get a factor of 2. This is using half precision, but not the tensor core, using the regular FMA kind of instruction. Again, another factor of 2. And that's what you get if you use the tensor core for doing the matrix multiply. Now that's a square matrix, and that's a large matrix, right? So that's the constraint there. Unfortunately for linear algebra, the dense linear algebra, I don't have that condition. I have matrices that I'm multiplying together which look like this. It's a rank K update to a matrix. That's the basic operation that I'm doing. And if I do that, I get different performance levels, single precision, double precision, using that half precision. And this is what I end up with on the tensor core, doing that kind of matrix multiply. So the performance drops, but it's still, of course, much better than before, but we got on the other ones. And doing the full LU decomposition using double precision, single precision, half precision using the FMA, and then using the tensor cores, you see the improvement there for that. So that's been embedded now into our library. Magma is capable of using that if you can. So we're interested in looking at algorithms which mix precision. They mix it in terms of using low precision and then trying to enhance the performance to get back up to the high precision. So that's going to be of interest. We get a lot of energy savings, and of course the time to solution is much better in that context. This is a well-studied algorithm. It's called iterative refinement for the solution of systems of equations. The algorithm proceeds as follows. You factor the matrix, doing LU factorization. You compute a solution based on the factorization. You compute a residual for that problem, and then you go into an iteration where that residual is used as the right-hand side, and you compute a correction to the solution. Right? So that's an algorithm that's there. It's a well-understood algorithm. You update the solution, you compute a residual, and then you iterate. The important thing about this is that first step takes the most floating point operations, n-cubed operations, and you can do that in lower precision. If you do it in lower precision, you only need higher precision for these critical parts, and those parts can be done with order n squared work. So we're going to leverage that low precision result using this iteration scheme here to get to the same accuracy if we had done the whole calculation in the higher precision. So there's a mathematical theorem that says that. There's some conditions on it, on getting the convergence, and the conditions are related to how well or badly conditioned the matrix is. So that's an important aspect, but it's important. It's a characteristic of the matrix itself to get there. So there's a number of ways to solve this inner system here. The classical way is to use LU decomposition. That is to use that factorization in computing that solution. Recently, Nick Hyam at Manchester and Lynn Carlson came up with a mechanism so that we don't have to use that factorization. We use an iterative approach using the preconditioner that we've computed using that LU factorization. So this step here is an iteration. We're inside of an iteration. So there's an inner and an outer iteration where the inner iteration does GMRES, right? That's an iterative process. We're doing it on a dense matrix. We have a very good preconditioner. So if things are right, this will converge quickly. The issue here is, if I solve this system here, the conditioning of the problem sort of limits how much accuracy I get. If I use GMRES, I don't have that same constraint in terms of the accuracy. So remember, I'm doing this in 16-bit arithmetic, or I want to do this in 16-bit, so I have to be careful about the conditioning of the problem. So that's the algorithm that we're going to look at, and this is the classic algorithm. This is using GMRES. The classic algorithm on a very well-conditioned matrix. The matrix here is of order. The condition is about size 100 in this case. So the way to read this is, we're going to be doing something using 16-bit or 32-bit accuracy. If we use, and remember, there's two ways of doing 16-bit on the Volta. One is using the FMA instruction, the other is using tensor core. So this orange thing here plots the number of iterations it's taken to converge, where we start with a 32-bit factorization. So the bulk of the work is done using 32-bit arithmetic. The green line here is charting where we do the bulk of the work using 16-bit arithmetic, using the FMA instruction, and the green is the tensor core, and this is using the 16-bit without the tensor core, just using the FMA instruction. So you can see the number of iterations it's taken. Fewer iterations, of course, you would assume would be faster, and I'll show you the times in a moment. This is doing the classic, and this is using iterative refinement using GMRES. So we got two iterations going on, the inner and the outer iteration, and everything is converging here in this case. It's converging to the 64-bit accurate answer. That's a very important thing to say in this context. So I start with a lower precision thing, and this is giving me the ability to go to a much higher precision through this iteration pattern. So here's the performance on that. So this is the performance for just factoring the matrix using 64-bit arithmetic. This is the performance where we do the factorization using 32-bit arithmetic and getting the solution correct to 64-bit. And I've adjusted the flops here, so we're counting it. We've normalized to the same number of flops, so I'm not, quote, cheating because I have more flops in the iteration. So you see the improvement in terms of the speed, in effect, the time to solution using 32-bit arithmetic. This is using 16-bit arithmetic using the FMA instruction. Again, the same accuracy is being achieved, but much higher performance associated with that. And that's using the tensor core. So we get a factor of 4 with exactly the same answer using the tensor core to do that factorization of the matrix. Okay, so this is a situation where the matrix is not so nicely conditioned, slightly worse conditioning, and in the single precision, single precision getting double precision results, we converge to a solution. Using the tensor core, because of that additional accuracy that you have, we're accumulating using 32-bit arithmetic, I actually get convergence, but if I use the 16-bit arithmetic, not using the tensor core, not getting that extra accumulation of accuracy, the method stagnates. Basically, it takes forever to converge. So that's a situation where it's not very interesting to use the method because the condition number is bad. So we see using GMRES, we see the same thing we're able to get here, and we're actually able to get to a better solution. That is, the convergence is done much better than using the classic method. So the GMRES is able to sort of wipe out some of the conditioning problems that's imposed in the matrix to get to a better solution. And again, here's the performance. That's 64-bit, that's 32-bit, that's using the half precision results with very slow convergence, and this is using the tensor core. Again, we get a factor of 4 using that tensor core. It has to be used carefully, I'll say, but that's one of the things. If we take a look at the energy that's consumed in doing this calculation, so we have tools, of course, to monitor the energy that's being used using a tool that we have called PAPI in this case. We get a picture. We get a picture like this. So this is the 64-bit accurate answer. This is a profile of the energy from when it was called to when it finished on that processor. We get 5.5 teraflops for the performance. We get 14 gigaflops per watt, and we consume 2,000 joules of energy to do that factorization. When we do the 32-bit arithmetic, doing the iterative refinement step, this is the iterative refinement step in the overall scheme of things. This is the factorization, takes the bulk of the time. We end up with something which is at 10, this is 32-bit, this is 10 teraflops, double the performance, 30 gigaflops, and about half the amount of energy that's needed to do that. And finally, when you look at mixed precision again, using that 16-bit arithmetic, using the FMA instruction, we end up with something again which is an improvement in terms of the quantities there, allowing you to effectively access the half precision for the factorization. And this is using the tensor core. So the tensor core, the factorization part is here, and this is the iterative refinement step that shows up in that. So we end up with 24 teraflops, 74 is the gigaflops per watt, and the amount of energy that's expended is 470 joules. So with that, I think I'm finished. I've got a few minutes, but here are the things that I'm interested in and passionately driven in terms of our work. We want to develop algorithms which reduce the amount of synchronization. Remember, we've got machines now that have close to 20 million processors in them, 20 million cores. And think about the way the way I originally learned how to do parallel processing was loop level parallel processing, fork join, coming down to one thing. I can't do that. I've got 20 million processors. I can't do the fork join. So we have to come up with better ways of doing that. Data flow, in my mind, is the way to go to relieve that. The second thing is communication reducing. Communication is one of the most time-consuming things on our processors. Moving data from memory to the processor is consuming a tremendous amount of time and also power, energy. We want to come up with algorithms which have the minimum communication that's possible. So there's a way to construct algorithms which have lower communication, perhaps even proving that this algorithm minimizes the amount of communication that can possibly be done. We want to mix precisions. I've just shown cases where we're using single, double, and half precision to improve our accuracy. We want to do that. We want to develop algorithms that effectively do that. Maybe having an inner and an outer iteration where you get an approximation in one and then refine it in the other step. Auto-tuning is critical. These machines are terribly complex, and I can't leave it to the user to adjust the knobs and switches on my software. I have to build that into my software and have it do that dynamically. As the program is running, have it adjust itself in some way. Fault resilience is also a key thing in the future. Coming up with methods that can recover from failure, a process failure, and carry on the computation, maybe by approximating something. Or that would be considered a hard failure. But think about soft failures where a bit gets flipped somewhere. You want to be able to detect that and potentially recover from that bit flip in a very natural way within the algorithm. So that's an important area. And the final thing is about reproducibility. Some customers demand that their answers are reproducible in the sense that if I run the problem today on my machine and I run the same problem tomorrow on my machine, I get exactly the same results. Now, I'm a numerical guy, And I know that's not going to happen in general. So on a parallel computer, I can't guarantee the order at which the collective operations occur. And if I can't guarantee it, I may get slightly different round-off errors if I add things up this way or this way. And the result of that may blow up if I have an ill-conditioned problem. So that's an issue. I can guarantee this, but it may cost. It may cost time in terms of guaranteeing that I do things in a certain way, the order in which the operations are done. And again, some people demand this, and that's something that we have to deal with, I think, ultimately. So that's my list of interesting problems to deal with as we move forward to exascale computing. And I'd be happy, I'm going to end there, and I'd be happy to answer any questions if there's time. So thank you very much.